So let me show you the agenda for today. So really what I want to do is I want to spend today reviewing what we talked about last week and the week before. We do have one practice problem we will try today. And then that's going to be it. There's not going to be actually an assignment for you to do today. So my plan is Wednesday to introduce the idea of universal gravitation, which we're going to use to talk about satellites and stuff. So we'll introduce that on Wednesday. And then Friday, which as of right now, it appears that we are going to be back in school on Friday. I'll give you some time. We'll do some practice together while you are here and I can answer any questions you've got. So that's kind of what we'll do on Friday. And I'm going to shoot for the test being the second to last class period before the end of the semester. So the date on that is, let's see here. The date on that is probably going to be December 14th for the test. So that's 2 weeks from today. But that'll give us a weekend class to prepare for that. All right, go ahead and if you would go to Socrative. So the website is www.socrative.com, and the code you need, you're going to log in as a student and you're going to use the code ROHRPHYS, ROHRPHYS. So if you could, either in a separate browser tab or on your phone, if you could go ahead and do that. And I will, if I can get to my chat here, I will put that in the chat. All right, and that first, you can go ahead once you're logged in there. You can look at that first question. So if an object is spinning in a circle, why does it feel like it's outwards, even though the centripetal force always points inward towards the center of rotation? So Parker, we're on Socrative right now, so it's www.socrative.com, and I'm sending you the code on the chat. All right. Give you guys maybe another 20 seconds or so to enter and answer what you think. All right, good. So the key is it's the object's inertia. There is nothing that pushes something towards the outside. It's the object's inertia that makes it feel like it wants to go to the outside, right? So if I could go to my document camera here for a second. We've done a lot with this notes page, right? Remember we said that circular motion is a combination of the centripetal force going towards the center and forward motion. The thing that keeps your forward motion is that you have inertia, right? Okay, so with that in mind, I want to move to the second one. So the second question here is asking about the game of tetherball. Let me go back to my screen here. So I don't know if you've played tetherball, but the idea of tetherball is you've got this ball tied to a string, and you are trying to kind of hit it back and forth. And the goal is to wrap the ball around the pole. But my question right now is just, if you've got a ball that is going in a circle like this, just in a level circle, which direction does the net force need to point? All right, let's see what we got. All right, so we seem to be favoring towards the ground or along the horizontal component of the tension force. All right, let me see if I can, I'm not actually sure that I can draw on this. Let me see here. No, I can't, so I will just go. So the idea, right, just from our earlier picture, right, we know if to go in a circle, you have to have a centripetal force that has to point towards the center. If you got a pole and you've got a ball going around the pole like this is a terrible drawing. But in essence, what you've got here, right, is you have a tension force that's going this way, and you have a force of gravity, but the tension force can be broken up into the x component and the y component. And the idea is the y component needs to cancel out gravity. It's the x component that is providing the centripetal force, right? Because it's the x component that's pointing towards the center. Whenever you're going in a circle, you need your net force to point towards the center. All right, next question. You are a passenger in the car, and the car makes a sharp left turn. From your perspective, what do you feel is happening to you? Good. So we pretty much agree, right? You feel like you're going towards the outside of the turn. So if you're turning left, you feel like you're being thrown to the right. Now, my next question is, which of these correctly explains why that's the case? During that sharp left turn, you found yourself being thrown right, hitting the passenger door. Which of these is a correct description of what's actually happening? Is a centrifugal force pushing you toward the door? Is the door exerting a leftward force on you? Or both of those, or none of those?
Your body still wants to move in a straight line after the sharp left turn.
I want you to enter your answer for this. You see what I'm saying, Nate? You're right, but I want to know which of these four solutions makes the most sense.
Oh,
Yes. This is one of my favorite questions. I want to see what we're saying. All right. So we almost all got it wrong. Now, could I actually, Nate, could I ask you to share what you're going to share? Because it's important in terms of answering.
Yeah, I thought you were asking for the last question. That's why I said that.
Fair enough. Yeah, but what were you going to say about it?
Oh, I was saying I thought you were asking for the left question, why it happened, and I had said because your body still wants to move in a straight line even though you're doing the left turn, so you're getting thrown against the door.
So the idea is you want to go this way, but the car gets in the way, right? It doesn't let you. So a moment later you were trying to go straight, but a moment later your car, like you're kind of, you just keep hitting the door. But what's really happening, right, is if you're hitting the door, what is the door doing? The door is providing a leftward centripetal force, right? So even though you feel like you're going to the right, to the outside, the only real force that exists is the inside force, the force that's pulling you towards the center. In this case, it would be a normal force, right? Be a normal force from the door. I want to talk about two vocabulary words, one we've used and one that you'll hear, but is not what we're talking about. There are two types of things that you'll hear people talk about: a centripetal force, and you'll hear people talk about a centrifugal force. So centrifugal, if you've ever heard of the word fugitive, right? A fugitive is somebody who's fleeing. A centrifugal force, this means a center fleeing force. And centripetal is a force that points towards the center. This thing does not exist. Centrifugal does not exist. It's what's called a fictitious force. It appears to exist, right? You appear to have some force pushing you to the right, but there isn't. It's just your inertia trying to make you go straight. What does exist is a centripetal force, and the centripetal force points towards the center, does not point towards away from the center, like a centrifugal force would. So you'll often hear people talk about a centrifugal force or like a centrifuge. So a centrifuge is something that spins really fast to separate something, to separate things. And in essence, right, a clothes dryer is a centrifuge because it's trying to like separate the water from the clothes by spinning. But the idea of centrifuge or centrifugal is misleading because there is nothing that's pushing it away from the center. What's happening is the object is trying to go straight and there's something that's pulling it centripetally in. So there's always a force that's pointing to the inside when you're going in a circle. There is never really a force that is pushing to the outside. This does not exist. Any questions about that? So that's why in this case, the correct answer was B. The door is exerting a leftward force on you, a force towards the center. All right, how about this? So these last few are gonna, I wanna think about what we were thinking about in class last time, and I guess it was on Monday when we were talking about more than one force causing a centripetal force. If you're on a Ferris wheel moving in a vertical circle, usually at rest, normal force is equal to gravity. How does the normal force change at the top of the Ferris wheel if I am currently in motion? So I'm currently in motion. What's true about the normal force at the top of the Ferris wheel? All right, so we tend to be right on that. The way to think about this, right, is with a free body diagram. So here I am on a Ferris wheel that's turning. We're going to say I'm going this way. I didn't draw a very good circle, but we're going to assume he's at the top, right? So if I were to draw a free body diagram, I need my net force always to point towards the center. In order for it to be a centripetal force, and in order for me to point towards the center, I need my net force to point towards the center. The only way to make the net force point to the center is for gravity to be bigger than normal. Now the opposite happens at the bottom, right? So at the bottom, again, now I need my centripetal force to be up. So if I was asking about this at the bottom, I'd need my centripetal force to be up. So in this case, I would need my normal force to be bigger than my gravity. All right, questions here? All right, next one. We got a skier here that's going over the top of a part of a circle, a hill that we were going to model as a circle. So which of these equations is a good representation of what the centripetal force would be equal to in this case? All right, good. Yep. Just to be complete here, I'll show this to you. We seem to understand this pretty well. But just to be complete here, the key is, again, in order for me to be going in this circle, I need my centripetal force to point down towards the center. And so I need there to be more gravity than normal. So when if I were solving this equation, right, the way I do this is I'd say centripetal force is equal to mass times centripetal acceleration. And the centripetal force would expand in this case to gravity minus normal equals mv squared over r. That's how you would solve that one. Very similar but slightly different one for this last, or third to last question. What about this time we've got a ball being swung in a circle. So at the top, what is true about the centripetal force at the very top? Okay. This is weird because this actually looks a little bit different than the other case, right? Let's go back to this here. So you got to remember, ropes cannot push, they can only pull, right? So when I was going over a hill, normal force was pushing this guy up. Well, a rope can't push anything. A rope only pulls things. So if I draw a free body diagram for this one, my tension has to come down because it's got to pull. And also, I have gravity going down because that's what gravity does, right? So in this case, my centripetal force, if I were solving this, would be equal to tension plus gravity. All right. For this next one, I want to start. I'm going to start by showing you a YouTube video. Maybe you've ridden one of these rides before. I was talking about a centrifuge a little bit ago. They do this. I don't know if you've ever ridden on one of these, but I want to show you this video clip real quick, and then we'll talk about it. I don't recommend actually doing this. All right, so I want to think about what's happening here, right? So for someone who's doing what they're supposed to be doing and standing against a wall, right? I want to think about the forces that are in play here, and that's what the next question asks about. So the next question is this. Imagine that you've got someone standing in one of these centrifuge rides, okay? So you're standing against the wall like this and it's spinning. And we're just gonna say that wall was a little tilted just for simplicity's sake. We're gonna assume it's a straight vertical wall. One of these is the correct free body diagram. So I want you to tell me which of these 5 situations you think is the correct free body diagram, but then I'd also like you to label it, right? So tell me, is the upward force normal? Is it gravity? Is it tension? All that sort of stuff, right? Same for the left or the down or the rightward force. So pick which of these free body diagrams you think matches the situation of somebody who's feeling themselves pushed back against the wall, and then label the forces. Let's see here. All right. So here's what I'm going to say. Just like the other ones we've talked about, again, centrifugal force, center fleeing force does not exist, right? That means we cannot have anything going backwards. What I'm actually going to say the answer is it's this one. I think it was one. This is the, oops, sorry, you can't see what I'm drawing. I'm sorry, just a second. So this is basically it, right? And I think we're all in agreement that this one should be gravity. It seems that a lot of people are wanting to say that this one is normal. However, remember, what does normal mean? What does it mean about the direction of the force?
It goes upward.
Not upward. Normal means perpendicular, right? Perpendicular to the surface. In this case, where's the surface? It's back here. That's your normal force. It should be, I meant to draw it horizontally. I messed it up, but yeah, that's the normal force. And in this case, the normal force is what's providing your centripetal force, right? Again, there's nothing pushing you back. It's just your inertia that makes you feel like you're being pushed back. But normal is pulling you in. Why am I not falling then? If upward force is not what's keeping me up, or sorry, if normal force is not what's keeping me up, what is keeping me up? I'm going to say it's friction, right? Friction is what, and this is why I remember I think I did this this example like one time. Give me 1 second here, right? I think I did this example when we first talked about friction, right? I talked about if I take an object here, I can push it against the wall and keep it from falling. And it's not what's keeping it from falling. It's not that I'm pushing in the wall. Me pushing in the wall is also causing the wall to push back on it. So it's increasing the normal force. Normal force is what causes there to be friction holding it up, right? So in this case, what I'm going to say is that it's actually friction force that's holding you up. It's normal force that's pushing you in. Again, there's nothing pushing you out. It's just your inertia that gives you the illusion of feeling like you're being pushed out. And this is what's happening in this case. All right, any questions here? All right, I'm gonna do one more question, and then this question is gonna lead us into one example problem, and then we're done. A 900 kilogram car makes a right turn of radius 6.8 meters. What force or forces is causing the centripetal force in this case? Remember, a sharp right turn is nothing more than a quarter of a circle. See what we got so far. Well, just give me, if you haven't put something in, just give me your best guess. Applied force of the car, friction and applied, normal, applied and inertia, force of gravity, force of friction, normal force. So I'm going to say of these things, and all these things are acting on the car, I'm going to say of these things, well, let's look, before I give the answer away, why is it bad to try and make a fast, sharp turn on ice? You know why it's bad to make a fast, sharp turn on ice?
There's no friction.
Yeah, there's no friction. The point is, right, you need to have enough friction to change your direction. I want to think about the forces that are acting on this car. In this case, and actually I'm going to draw a couple pictures here. I'm going to try and draw a 3D view here, right? So imagine that this is the ground and the car is kind of trying to turn this way, right? Let's think about the forces that are acting on the car, right? You've got gravity that's going to be pulling straight down, which I'm drawing this one's a hard picture to draw. But if I wanted to draw it in this picture, right, I would have to go into the paper. So I'm just not going to draw it there. So I'd have gravity. I'd have normal. And on this picture, right, my normal would be like coming up out of the page. Those two, neither of those can do anything in terms of giving me a centripetal force. I need something that points towards the center. I also saw applied. What is the applied doing? Well, if you are going forward, right, the applied force is what's allowing you to go forward. So on my top-down view here, right, my applied force would be going something like that. Then I might have sort of air drag, or what I'm going to call, so I'm going to draw maybe some air drag here, going backward. And maybe you've got some friction going this way. But really, the friction that's causing me to turn is the friction that points this way. So here, I'm going to point it towards the center here. This is what's providing the centripetal force. The friction is the thing that is providing the centripetal force. Now, you might have some friction. So really, what I should say is I should say that friction has two components. I would call this the centripetal component, and I might call this the tangent component because it points tangent to the circle. But in reality, the only thing that can provide any centripetal force is friction. So we're going to say friction is providing the centripetal force in this case. Okay? I would like to end real quick with an example problem like that. And you don't have to do this with me. I just want you to see real quick how I could answer the question. If I ask, like, I have a 900 kilogram car that makes a right turn of radius 6.8 meters, and let's say that I told you the coefficient of friction was 0.72, and I want to know how fast is it going, right? How would I do that? Well, the way I solve every problem is I say the centripetal force is equal to mass times the centripetal acceleration. We know centripetal acceleration is v squared over r, but in this case, what did we say the centripetal force is equal to? Friction, which is mu Fn, right? Or in our case here, right, we know that normal force is the same as gravity. So once again, we could say mu mg equals mv squared over r, and I could show my m's canceling out, and that would be how I could solve this. Any questions about that? Okay, we're coming up on the end of the period real quick. I just want to give you an overview of what's coming up. So we'll do a little bit more notes next class, and I do think I'll have a daily assignment next class. There's no daily assignment today, but we will have a daily assignment next class. When I see you Friday, which at this point looks like I will be seeing you in person on Friday, that day is going to be spent doing all the kinds of practice problems we've done so far, so that you can do it while you're there and I can talk to you face to face. And then we will continue as usual on Tuesday. And I will give you a shortened syllabus because we've essentially done much of the syllabus in terms of our daily assignments. But that's sort of what's coming up. But that's all I got for you today. So enjoy the rest of your afternoon, and I will see you on Wednesday.